Hello everyone, welcome to Megger's monthly webinar series. Today's topic is understanding power quality testing. In this session, we will be discussing the common power quality phenomenon that can be found on the modern grid, its causes and effects, measurement, and how to perform a power quality analysis. My name is Greg Valdez, and I'm the Marketing Communications Manager for Megger North America. And I'll be acting as a moderator for today's presentation. I will be supporting you on any technical issues or questions for our presenter during the session. On the right hand of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during our Q&A segment. You will receive a copy of this presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation and we will answer them at the end of the presentation today. Our presenter today is Andy Sagel, Megger Product Manager. Andy is based out of our Valley Forge office in Pennsylvania. Thank you for joining us, Andy.
Thank you. And what I'd like to do is just start off with one simple question. What is power quality? Okay. Power quality is the concept of powering and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. That is basically the definition per IEEE. Okay. Now, today, the modern grid, we're seeing a lot of changes happening in it. You have the addition of green energy sources such as solar and wind. We're seeing a reduction in the coal bulk generation plants. And we're seeing new loads. And as loads increase, coupled with the intermittent nature of the solar and wind energy, we're seeing variability within the actual RMS values that we're seeing. Okay. Then we have new technologies that are coming in. Electric vehicles adding new loads at new times so we can see altered peak hours eventually. And we're also seeing the implementation of smart grid technology, which is basically increasing the communications that we see across the grid. So we are seeing many changes today. And one of the things that I've been asked is, will smart grid reduce power quality issues? And the simple answer is no. The smart grid is meant to increase grid reliability, not the quality of the power being delivered. In fact, as these technologies advance, there will always be new types of loads and sources that get added to the grid. And this will create new power quality challenges that we're going to see. And as we see more solar and more wind, we're going to see more power quality issues approaching. As solar gets added, you'll see higher voltages and unbalance and transient issues. And as of today, the most common power quality issues we still face today include sags, swells, transients, unbalance, as well as harmonics. And what I will be covering today is we're going to cover undervoltages, overvoltages, dips or sags and swells, transients, unbalance, flicker, harmonics, RVC, which is rapid voltage change, and also we're going to cover the proper way to perform a PQ analysis. Okay. Let's first start with the undervoltage. And undervoltage is a decrease in the RMS voltage less than 0.9 percentile units for a duration longer than 1 minute. Okay, and that would mean if your voltage, for just ease of calculation, if your voltage is 100 volts, an undervoltage would be under 90 volts for over 1 minute. And typical values for these are between 0.8 and 0.9. Okay, undervoltages are caused by load switchings or capacitor banks switching off, and they can cause problems such as equipment tripping offline or failing. And an undervoltage can actually continue until voltage regulation equipment on the system kicks in. And also overloaded circuits can cause undervoltage issues. Okay. Overvoltage, An overvoltage is an RMS increase in an AC voltage greater than 1.1 percentile units for a duration longer than a minute. And typical values for these are 1.1 to 1.2 percentile units. Now, overvoltages can result from switching loads as well, reactive compensation, but also today we're seeing a lot of overvoltages being caused by solar tiles being installed on the systems. And this can create overvoltages, which we're going to see later on, can actually cause many problems, especially with motors failing and burning out prematurely. Voltage sag or dips. You can hear these referred to interchangeably, because here in the United States we tend to refer to them as sags, where in other areas of the world they will be referred to as dips. And it is the exact same thing they're talking about, just different terminology. And voltage sags and swells, they're the two most common power quality events. The sags and swells, they can't be prevented on power systems. As impedance change, you're going to have changes in the voltages that responds to those changes in impedance. Even instantaneous short duration sags, though, can cause processes to shut down. And when processes shut down, they can take hours to restart. And in fact, you can lose an entire production run. So they can be very detrimental and very costly to manufacturing facilities. Voltage swells, they're the most common cause of tripping breakers. And again, with solar tiles in there and you're seeing increased levels, you're going to be seeing more breakers trip and more equipment failure, tripping offline. All right. Now, a voltage sag, they're caused by abrupt increases in loads, such as short circuits or faults, or more commonly, motor startups. Okay. As the motor startups, we get a large inrushing current. And as you get that big inrushing current, the current goes up, the voltage goes down. And that's typically where we'll be seeing those voltage sags. So typically, if we see a current going up and a voltage going down, we know it's on the load side. Now, you can also have a sag from the source side. If you have a short on the source side, and you'll see the voltage go down and the current go down both at the same time. And then you can see that that's basically happening from the source side. Now, voltage swells, they're pretty much caused by abrupt reductions in the load or the impedance. With a poor, you can have poor damaged voltage regulators, and these can also be caused by loose neutral connections as well. And again, with these, if you see the voltage swell and the current drop, that's an indication that someone turned off a load. And we know that's on the load side. If we see the voltage swell and the current swell, then typically that's more from the source side. We're seeing a voltage swell, which is increasing the current on the load side. Now, sags and swells are categorized in different ways. So you may hear different terminologies for them. There is the instantaneous sag. This is a short duration variation which lasts from 0.5 cycles to 30 cycles. The voltage during an instantaneous sag will vary from 10 to 90%. That's what we refer to as instantaneous sag. Now, we also have an interruption. An interruption will last from 0.5 cycles to 3 seconds, and the voltage will fall to below 10% of nominal. Okay. We also have what's referred to as momentary sags. It's a short duration variation that lasts from 30 cycles to 3 seconds, so it's longer than an instantaneous. And the voltage drops to 10 to 90% of nominal. And a temporary interruption, this is an instantaneous sag. Now, an instantaneous sag is a short duration voltage variation that will last 3 seconds to 1 minute, or a temporary interruption lasts from 3 seconds to 1 minute, and it will drop to less than 10% of nominal. This here is just actually showing a visual format of the different categories of your different types of sags and swells, and they are categorized based upon the percentage of nominal and how long they last. So when you hear them referred to, you know what type of event or what type of sag is being they are talking about, especially in the standards, because that is how they are referred to. Now, transients. Generally, there are two types of transient overvoltages. We have a low frequency transient and a high frequency transient. The low frequency transient is typically in the few hundreds of hertz, and is typically caused by capacitor bank switching. They're also referred to as oscillatory transients. This is what we see in the bottom image there. And they're categorized by the ringing effect that you see. And we also have the high frequency transients with frequency components in a few hundreds of kilohertz. And these are typically caused by lightning or inductive load switching on. Now, they're going to be characterized because they're basically single-ended, and you don't see the ringing out on them. Okay. Transient voltages can result in deterioration or immediate dielectric failure in any class of equipment. You have high magnitude and fast rise times, which contribute to insulation breakdown. And you can either have a very severe transient that causes an instantaneous breakdown, or repeated low magnitude transients will slowly degrade the insulation. And over time, you will get a failure in that insulation. And when we look at wire or cable, it's not much different than a capacitor. Basically, in a capacitor, you have two plates or two conductors that are separated by an insulator. In a cable, we have the shield and the center conductor, which is also separated by an insulator. So we basically have a capacitor there. And the longer the cable is, the more surface area you have, the higher the capacitance you have. And basically, we can understand how damaging the transient can be to the insulation based on this simple capacitor reactance formula. As the frequency goes up, the capacitive reactance goes down. So the impedance of the actual path across the insulation goes down. So basically, the higher that frequency or the higher the magnitude, the more destructive it will be to the insulation of the wiring and also motors, transformers, anything that has insulation. Now, a transient acting on a coil within a motor or a transformer will dissipate the majority of energy in this first few coils. Each successive coil presents more resistance and tends to degrade the transient, dissipate it. So since the majority of the energy is transferred in the first few coils, what we can see is that this is where we'll typically see the damage when it's due to transients, will be in the first few coils of the motor. Now, transients don't only just affect motors and coils, they also have effects on lighting, and they can have effects on fluorescent lighting. As you get transients that come through, they will actually cause dark spots on the fluorescent lighting. Now, a fluorescent light illuminates because the gas inside the light is ionized when a voltage is applied across the electrodes. When you have transients that are repeatedly applied to fluorescent lights, you get mercury deposits on the actual lighting. Okay, so you have material that gets displaced. This will reduce your lighting, and eventually it reduces the lifespan of the fluorescent light, and you'll have failures that will appear. Now, typically, when a fluorescent light fails, you'll see darks. It will get dark on the edges. That's normal, but if you start seeing spots on it, that's a sign of transient issues that are occurring. Now, lightning is a major cause of your impulse transients. Now, a bolt of lightning can be over 5 miles long and reach temperatures in excess of 20,000 degrees Celsius. It's a bit hot. And lightning strikes, they produce very large electromagnetic fields. These fields, when they cross over the wires, will induce the transients on those wires. So you just need to be in the general proximity, and you will see the transients on the wires. And of course, these are much worse if the grounding is not set up properly. And these now, the typical characteristic though is they're typically seen as unidirectional transients. So they go in one direction. When a cap bank switches, there is an initial inrush of current. This leads to the low frequency transients that have that characteristic ring in them. And these types of transients are often referred to as oscillatory transients. Oscillatory transients can cause different types of problems too, especially in UPS systems, where a UPS system is basically sold on how fast it can respond to a change. And when you get an oscillatory transient that occurs, you can actually have UPS systems turning on and off rapidly multiple times. And you'll see this throughout the day as loads are turned on and off. As the loads are turned on, cap banks are switched in to compensate for the inductance of the loads, and you get these ringing events that occur. UPSs can switch on and off quite frequently. And one of the things to do to correct this is lower the sensitivity of the UPS so that you don't have it constantly switching on and off, because they do have a limited lifespan based on how often they turn on and off. So let's go to unbalance right now. Unbalance is a condition in a polyphase system in which the RMS values of the line voltage, the fundamental components, or the phase angle between the consecutive line voltages are not equal. A voltage imbalance more commonly emerges in individual customer loads due to phase or load imbalances. And this is especially true where you have large single-phase power loads that are used, such as single-phase arc furnaces. And keep in mind that a small unbalance in phase voltage can cause a large unbalance in phase current. This can be a difference of 6 to 10 times. Okay, so when you see an unbalance in the voltage, if you have a three-phase motor, you may see a 1% unbalance in voltage. This can represent up to a 10% unbalance in current. This, when you have more current going through that motor, you're generating more heat. As you generate more heat, you're deteriorating that motor. This is one of the things that you can see with solar tiles when they're hooked up, if they are only put on one phase. Now, as I said, unbalanced voltages can affect equipment on power systems such as induction motors and adjustable speed drives, and it causes these heating effects due to these higher currents that we see. Now, how do we actually measure unbalance? Right? In the past, we used an ANSI method where you would look at the phase-to-phase voltage, determine the average of them, and then you would compare each phase to that average. Now what we do is we use symmetrical components to measure unbalance. And the symmetrical components will change as the magnitudes of the individual phases change or their phase relationship change. Now, what do I mean by symmetrical components? These are basically our sequences. We have a positive sequence, a negative sequence, and a zero sequence. When I refer to these sequences, what I am basically referring to is the rotational components of the magnetic field. Okay? In a perfectly balanced system, both negative and zero sequence would not exist. So when we talk about the actual sequences, we're talking about the rotation of the magnetic field. Positive sequence means that the magnetic field rotates in the same direction as the fundamental. A negative sequence means the magnetic field rotates in the opposite direction of the fundamental. A zero sequence means it has no phase rotation, and they will tend to add together and add up onto your neutral. So the benefit of being able to look at your unbalance through phase sequence is you can see very quickly the negative and zero sequence unbalance. The negative sequence unbalance will act as a resistive component to motors. It works against their torque, and that will generate heat in them. Zero sequence, on the other hand, can create very high neutral currents. So by looking at these unbalance factors, we get a better idea of how that unbalance will affect the system. Now, how do we calculate this, though? The sequence components are calculated based on Fortescue's principles. Basically, what we're doing is we're shifting the phases B and C 120 degrees and 240 degrees respectively. And any changes will be seen in that. Now, for a positive sequence, if I shift phase B 120 and phase C 240, basically I'm going to still end up with being able to see three phases. That's what I'm showing here. So if I look at the upper chart, I'm seeing a phase rotation of A, B, C. When I switch them, I'm still seeing the three phases as A, C, B. So they're all still there. So you always have positive sequence. However, when you look at negative sequence components, you're shifting phase B by 240 and phase C by 120. What happens then is they cancel out. So if you have a perfectly balanced system, you will have no negative sequence. But if there's a difference in magnitude or phase, you will see negative sequence unbalance. And the way we look at it is as a sequence factor. We always compare it to the positive sequence. So if I have negative sequence unbalanced components, I'm going to compare it to the positive sequence and multiply it by 100. This is what's referred to when you look at your negative sequence factor. It's a percentage of the positive sequence. And the same with the zero sequence factor. It's a percentage of the positive sequence. So this is how we're looking at unbalanced factors. Flicker. Flicker is something I get a lot of questions on. Flicker is a very specific problem, and it is related to the human perception of an incandescent light bulb. It is not a general term for voltage variations. When we refer to flicker, we're referring to light variations. And humans can be very sensitive to light flicker, which is caused by voltage fluctuations. Basically, studies have been done to show that when they tested incandescent lights at 50 hertz and at 60 hertz, at 120 60 hertz and 230 50 hertz, and they have changed the magnitude of the voltage and the frequency at where it actually changes. And what was found was that when the rate of flicker approaches about 8 hertz, the human eye is most sensitive to it there. So it takes a very small change in magnitude at 8 hertz for flicker to start being noticeable. And it can, as the magnitude increases, it gets irritating, and then it can actually get painful. As the frequency of the flicker deviates away from 8 hertz, below it or above it, the magnitude of the voltage fluctuation has to increase for it to become noticeable. In fact, when it gets above 30 hertz, it's flickering so quickly we don't see it anymore. Our eyes don't pick it up anymore. But because of this allowed us to come up with a flicker measurement using what we refer to as an IEC method. IEC 61000-4-15, which has now been adopted by IEEE 1159. And this method, what it does is, because they know how the human eye responds to the different frequencies of the flicker, they were able to create a weighted curve. That weighted curve is based upon the eye's sensitivity to an incandescent light at 120 volts 60 hertz or 230 volts 50 hertz. By using the weighted curve and looking at how often the light flickers and the magnitude of it, they can calculate what we call a percentile unit. And the percentile unit then goes through a statistical analysis to come up with two values. So basically what we do is we look at a rolling average of the RMS. We look at how often it's changing and the magnitude, and we come up with the percentile unit. That percentile unit then goes through this formula, which is a statistical analysis, to come up with what is referred to as a PST value, or a short-term flicker value. This is based on a 10-minute interval. We also have what's called a long-term flicker value, PLT. Basically, this is calculated using the short-term flicker, and it's based on a 2-hour rate. Now, with all that said and done, it sounds complicated, but it comes down to something very simple. If you're using an incandescent light, if the PST is greater than 1.0, then the flicker levels can be causing irritation. For the PLT, if the PLT is greater than 0.8, it can be causing irritation. So all that methodology of how it's done comes down to a simple 1.0 or 0.8, depending on what you're looking at. The important thing to keep in mind is this is related to incandescent lights. When you try to use flickers to measure other types of lighting or equipment, you have to keep in mind that the weighted curve is designed for an incandescent light. So although you will get values, how those values relate to everything is sort of unknown. In fact, there are studies being done at present to see how flicker values can be used for fluorescent fixtures, CFLs with magnetic balances, the compact fluorescents with electronic balances, halogens. This testing's ongoing, so there is no direct correlation to it for these types of lighting. But there's other things that can actually cause, flicker is typically caused by other events such as RVC and interharmonics as well, and we're going to be covering the RVC in just a little bit. Before we get to the RVC, let's go into our harmonics first. Okay, there is a lot of talk about harmonics and where we're going, because as the grid is changing, we are seeing higher frequency levels of harmonics coming out. In the past, we were really looking at harmonics about the 15th order and down. Nowadays, with the higher switching frequencies of inverters, electronics, LCD TVs, we are seeing harmonics roughly from the 35 to the 45th order appearing. Okay? And let's first ask, what are harmonics? Harmonics are a sinusoidal component of periodic waves that have frequencies that are multiples of the fundamental frequencies. They can cause problems such as neutral wires overheating, motors to overheat, transformers to overheat, and of course electronic failures, you will see. Now, linear loads such as incandescent lights, such as motors, when they operate, they draw currents equally throughout the waveform, so they do not create harmonics. However, today we see many more nonlinear loads, and they are ever increasing. Nonlinear loads, such as the switching power supplies, draw currents only at the peak of the wave, so they do not draw current equally throughout the waveform. It is the nonlinear loads that cause these harmonics. Now, typically, if we see current harmonics but not voltage harmonics, these current harmonics won't propagate through a transformer, they won't propagate through the system. However, when current harmonics get large enough, they will start affecting the voltage. In this image here, what you're seeing is that as that current harmonic goes up, we're seeing what's called flat topping, or a third harmonic on the waveform. This is showing us that our source isn't stiff enough to maintain the voltage during this current. And it's these nonlinear loads that will create our harmonic distortion. Now, voltage harmonics will propagate through a transformer and get through the system. When we talk about harmonics, there's different ways that we can categorize them. One method is to look at odd and even harmonics as well as triplets. Odd harmonics are simply that. They're harmonics with odd orders. When I refer to orders, I mean that the numerical order of the harmonic, which is basically, if I look at the fundamental at 60 hertz, that's my first order. A second order would be 2 times 60 or 120 hertz. Third order, 3 times 60 or 180 hertz, and etc. and so forth. And of course, 0 would be DC. So when I look at my odd harmonics, I'm looking at my odd order odd numbers, like 3, 5, 7. When I look at even harmonics, I'm looking at my even numbers, 2, 4, 6. And triplets are a special case of odd harmonics where they are multiples of 3. Now, why do I care about any of these? Odd harmonics are natural. These are the things you're going to see on the system. And these are caused by your nonlinear loads. And one of the things you'll notice from the picture on the left is that they are symmetrical. When I look at even harmonics, though, 2, 4, 6, these, if you look at the middle picture, you notice they're not symmetrical. They are not really supposed to be on the system. When we see even harmonics, that's a sign that we have a bad rectifier somewhere in that system. So we're not getting, that's why we're seeing a non-symmetrical waveform with them. Even harmonics, they typically should be limited to about 2%. If they are above 2%, IEEE 519 typically will flag that as a problem. Now, triplets, or odd harmonics that are multiples of 3. These type of harmonics do not cancel out with any other frequencies. They actually add together. So triplets will cause high currents on your neutrals. This is why in the past, neutrals used to be quite thin. Now, if you look, neutrals can be even larger than the primary leads. Now, harmonics can be categorized also as sequences, again, based on their magnetic rotation. Positive rotating in the same direction as the fundamental, negative in the reverse direction of the fundamental, and 0 has no rotation. So, if I have a negative sequence harmonic that's rotating in an opposite direction of the fundamental, these can cause heating effects in motors because they're going to resist the rotation of the motor. If I have 0 sequence harmonics that have no phase rotation, these are like my triplets. These will add together and we'll see them as high neutral currents. And how do I know which harmonics are positive sequence, which are negative sequence, which are 0 sequence, which orders are what? It's actually relatively simple because if I look at the actual numeric orders of it from 0, 1, 2, 3, 4, they follow a sequence where 1 is considered a positive harmonic. That's my fundamental. 2 would be a negative sequence, 3 a 0 sequence. Then the order repeats. So 4 is positive, 5 is negative, 6 is 0, 7 is positive. So if I was to look at something like the harmonics from a 6-pulse converter, I would see a majority of 5th and 7th harmonic there. So the 5th harmonic would be a negative sequence harmonic, and I know this can create heating effects in motors because it resists the turning, the rotation of them. And the 7th harmonic I know is a positive sequence harmonic. So by looking at these, I can see how they can affect the equipment that is on the network or on my system. And of course, triplets or zero sequence harmonics can cause neutral lines to overheat. And this is again because they do not cancel out. When I have different frequencies of harmonics, basically at some points the peaks and valleys can cancel out. But in triplets or zero sequence, that will not happen. They are in phase and they will grow, and this is why we can see such high neutral currents. And again, this is just referring to what we see as we have high neutral currents. Right here, I'm showing a neutral current with no harmonics, and as soon as I start adding ninth or third harmonic, I can see neutral current showing up. As soon as I add a ninth to it, they are adding together. I'm getting a greater magnitude on them. Now, harmonics, they cause heating effects in coils, transformers. Well, this is referred to as winding loss. It's also known as copper loss, and it will create these harmonics. This is because as AC current goes through a wire, it creates eddy currents within that wire. Those eddy currents are small circular currents, and they produce magnetic fields that oppose the magnetic field of the current going through the wire, so they create resistance. What that ends up happening is they will actually push the current that's going through the wire toward the outside of the wire. This is what's referred to as skin effect. So basically, as my harmonics increase, the current is being pushed more and more to the outside of the wire, which means I'm losing cross-sectional area of the wire, which means its resistance is going up, or I should say impedance is going up, and heat is going up in it. So when this occurs, the motors, the transformers, they can degrade. Now, it's not just the amplitude of the harmonic that matters, but it's also the frequency. The higher the frequency of the harmonic, the greater the heating effect as well. Now, we can look at all the different harmonic values. We can also look at total harmonic distortion. Total harmonic distortion is just a measure of the sum of all the harmonic components of a distorted waveform. Now, THD, total harmonic distortion, can be calculated for either current or voltage. However, you do need to be careful with this. Is that THD is the root mean square of the sum of the harmonics divided by one of two values, either the fundamental value or it can be shown as an RMS value. If it's divided by the fundamental value, it's going to be shown as percentage of fundamental. Otherwise, it can also be shown as actually an RMS value itself. Now, as I said, THD can be misleading because I can look at voltage THD, and since the voltage is pretty much always present, I always have a good reference for the THD value. So just for ease of calculation, if I have 2 volts of THD and 100 volts there of fundamental, I got 2% THD. But how does that work with current? If I look at THD for current, well, if I'm drawing current, if I have a good load, THD will work. So, but if someone turns off the load and I'm not drawing a lot of current, that THD value can be misleading. Okay? If I look at a total harmonic current, let's say it's 0.2 amps, and the fundamental current being drawn is 200 amps, THD is 3.16%. However, if the fundamental current being drawn by the load drops to, say, 200 milliamps, the THD will equal 100%. So you'll look at this THD value and go, oh, I got a problem here. But in reality, you don't have a problem because there's no current being drawn. So What we recommend, and what IEEE 519 recommends when you're looking at current distortion, total current distortion, to look at what's called total demand distortion. Okay? Total demand distortion refers to the total root sum square of the harmonic current distortions, but instead of being averaged to the current value at the time the measurement's taken, what we do is we look at the entire recording interval, and we pick the maximum average current that was drawn during that interval and use that as a reference throughout the entire test. That means that the TDD value for the current always has a good reference and will give you the proper representation of your actual distortion on that line. There's also some places, some utilities actually have their own reference value they plug in for TDD values. And again, for THD and TDD, as well as your harmonics, it is recommended to go and get the IEEE 519, and this will have a tremendous amount of information on it, as well as what their recommendations are for your low and medium voltage systems. Now, let's get to RVC, or rapid voltage change. A rapid voltage change is a fast rise or fall of the RMS voltage. And what we're seeing here is with the advent of green energy, renewable energy, you have solar tiles, wind, all these things don't produce continuous energy. As the clouds go in front of a solar tile, its output changes rather dramatically and quickly. When you look at a wind farm, as the wind changes, its output changes. This can create rapid fluctuations in your RMS voltage. And now just a reduction in voltage to 10% can result in a 34% reduction in light intensity. So a lot of this can be seen from complaints of lights flickering. And this will especially be seen where you have a potentially weak network. And again, this is typically caused by sources that change. This can also happen if you have loads that are changing very quickly, but more commonly it's going to be a source side issue. Now, a rapid voltage change, and basically the event starts with a steep downward step followed by an upgoing ramp, and that steep downgoing step can be as quick as 10 milliseconds. One of the things to keep in mind is for an event to be categorized or classified as a rapid voltage change, it cannot deviate so much that it goes below the dip or the sag threshold. If it does, then it's a sag, not a RVC. An RVC is typically a change in voltage of about 3%. And not typically we would set our limits for a sag at about 10%. Now, how do I capture rapid voltage change events? Well, in order to capture a rapid voltage change event, we first need a nominal voltage, or the declared voltage. Then a threshold is defined. Typically that threshold is about 3%. Now, we also have to look at a hysteresis value for this as well. The hysteresis value, well, let me first say that, let me go back for a second there. The threshold, like I said, must be set at 3%, or that's the rough approximation where it approximately is. In order for a rapid voltage change event to occur, an RVC event, you first have to get to a steady state. And that means that the voltage must remain constant for at least a second. Once you have achieved that steady state, then you can have a rapid, then it will look and see if the voltage changes by 3%. If it does, an RVC event can begin. The RVC event will not stop until the voltage comes back within 3% plus a hysteresis value, which is typically set at 10%. And this must be maintained for another minute to get a steady state. So when you're looking at rapid voltage change, it's a smaller change than a sag, and steady states are required. So this is what differentiates it from a actual sag or a swell, which is a momentary event. Rapid voltage changes can happen continuously and be quite small. All right. So with all that said, now let's go into how do we actually conduct a power quality investigation to find out what the problem is. There's several steps that have to be followed. And one of the most important things is to plan and prepare for it. We need to ask questions when we're troubleshooting something. What is the reported symptom? How often does the symptom occur? Very important question, because this is going to define how long you're going to do a recording for. Can any patterns be recognized? Can any correlations be made from those patterns? Has there been any changes to the equipment on the power system? A lot of times you can get a big clue from that. If something has been recently changed and suddenly there's a power quality problem, that's a good shot that they're related. And the other thing is to receive inputs from as many people involved as possible, because different people may be seeing things a little bit differently. And it's sort of like conducting a criminal investigation there. Question as many as you can. Inspect the system. First of all, check for safety hazards. Check everything's to code. A lot of times that can be an issue. And check for bad connections. Thermal imaging actually does come in handy for this, to look for a hot spot. Now, you can hook up a monitor and you can do some immediate checks right on the spot. You can look at your harmonics right on the spot, your unbalance on the spot, and you can look at instantaneous flicker, you can also look at interharmonics and things like that, which I actually didn't cover. That would be in another session. If you don't find the problem right away, you may need to do some monitoring. So one of the first things we want to do is select the proper location. And typically, there's several points. One is if I'm troubleshooting a house and I want to know whether the problem's on my side or their side, I need to go to the point of common coupling. So whether it's a residential or industrial location, that's probably my first point. However, there's also the case where I might be looking at a particular piece of equipment that's tripping offline. If I'm doing that, I want to get as close to the failing equipment as possible. Especially now if I'm dealing with motor issues, I want to get as close to the motor as I can. Because long motor leads, if you have long motor leads, they can create problems in themselves. Because remember what we talked about before, about the capacitance in a cable? The longer the lead, the higher the capacitance is. So if I'm measuring at the end of the cable furthest from the motor, I may see relatively small transients there. And that may not lead me to know that there are problems. As I get closer to that motor, I may see those transients get much larger due to the interaction of the magnetic field of the motor to the capacitance in that cable. So try to get as close to the equipment that's failing or tripping offline as possible. Okay? Take your environment into account when you're doing a test. Verify the instrument you're using is rated for that temperature, moisture, and humidity levels. Also, we want to make sure we select the proper current transducer. We want to make sure we've determined that we have it the proper range. If you select a current clamp where the range is too low and the current goes up too high, on a split core you may saturate it. All right? If you select a current range that's too high, then what end up may happening is you'll get poor resolution on them. So we want to try to get the proper current range selected within a given area. Now, there's also the question of, do I use a flexible or do I use a split core CT? And one of the first questions you have to ask is, logically, does it fit in the location? Okay. And if you're going to use now a split core has some benefits to it because it has an iron core. So it's high permeability. So basically these are very good when you're doing low current measurements. Okay? If I have to hook up to a secondary, then I may want to use a split core. If I am going to use a flexible CT, they have some benefits too, in the fact that they can get around larger bus. They are easier to get into tight locations. Okay. But they're also air core Rogowski coils, which means they have low permeability, so that they're really not recommended where you have low current values you're measuring. And by low current values, I'm talking down around 10 amps or lower, because you may get a good magnitude on them, but keep in mind your phase shift, because they're air core, can gain in inaccuracies, and accuracy can go up. Other questions to ask is, does the area have a high EMF? If it has a high EMF, you may want to go split core. And the other big thing, are you recording DC? If you're recording DC, you cannot use either a split core nor a flexible CT. In that case, you need to use a Hall effect CT in order to measure DC. So selecting the proper current clamp is critical. And also keep in mind, if you're going to use a flexible CT and you're doing a recording outside, not only does the monitor have to be weatherproof, CT does as well. Okay. Now, we have the monitor set up. We're ready to go. We have it there. Now we have to actually make sure that it is programmed properly. We want to make sure we have it set up for the proper power configuration. The proper event triggers are set. Different problems can be caused by different PQ phenomena. Want to make sure we're looking at the right things. Want to verify our CT range. We may want to consult with application notes, or what even makes this easier is if you have a software anywhere that actually uses a wizard to actually help you create the actual configuration. And this will allow you, those type of things allow you to create custom configurations to find particular PQ phenomena or PQ problems. Okay. Monitoring. You need to connect the PQ analyzer. Number one, make sure you have the proper protection equipment on. Always take safety first. Okay. Verify the voltage leads are connected per the power configuration diagrams. Verify the CT ranges are set correctly. If you're using flexible CTs, they can have multiple ranges on them. Verify the CTs are in the proper direction. Okay. Verify that the unit is powered properly. Some units can be powered off phase A or auxiliary power. So you want to make sure everything's set and connected properly. Ground the unit for safety. And if you're leaving it outside, lock it up. Too many times you can go back and find it's not there. So, we have it hooked up. We're getting ready to record. We always want to review that data before starting that recording. Some of the things we want to verify is we're going to verify the RMS voltage and current values are being read properly. Verify the KW is positive. Okay. If the KW is negative, that's an indication that we have a CT that is backwards. And verify the phase angles are correct per the connection diagram. When I look at a voltage angle versus a current angle, they need to be within 90 degrees of each other. If they are not within 90 degrees, there is an issue. Okay. Now we're going to record that data. Before you leave, verify the unit is recording. How long do I leave the unit there? One of the questions we asked in the beginning was, how often does this problem occur? We want to leave the unit for at least one complete cycle. So if the problem happens every couple of days, the recording should be at least 2 days. If the recording happens only once a week, apparently, you want to leave it for at least a full week to try to capture the event that is causing the problem. Now, we have the data. and we need to analyze it. So one of the first things we look at is, did the failure repeat itself during the recording interval? If so, when did it happen? We look at that data right at that spot to see, did we have any dips, swells, transients? Did we have high harmonics, THD events that occurred at that point? Was there a rapid voltage change that occurred at that point? All these things can tell us something about what caused the problem. And data analysis software can be very helpful for this, because a modern power quality analyzer, keep in mind, can record an enormous amount of data, which can make the actual analysis can be cumbersome. So data analysis software can be helpful in finding problems quickly. Now, with all that said, what I would like to quickly just show you is our latest power quality analyzer, the MPQ-2000. This is a 9-channel indoor-outdoor unit. It can be powered off phase A or auxiliary. It has up to 5 hours of battery backup. It will auto-identify the CTs, not just the CTs that are connected, but also the range that they are in. It also does configuration verification to make sure that it's connected properly before you start the recording. As I said before, when we were going through how to set up a recording, we always check the phase angles, and we want to check that the KW is positive. So it's always a good practice to do, but if you do make a mistake, the unit will let you know something's wrong before it starts the recording. It will let you know something's turned, so CT is backwards, or the phases are hooked up wrong. It also has a built-in data analysis, both in the PC software and on the unit. So you can actually do an analysis right on the spot after the recording is done. It has a built-in scope and DMM mode, digital multimeter mode, so you can actually look at waveforms, vector diagrams, harmonics, interharmonics, unbalance all in real time before you even start a recording. So you may actually find a problem before you actually even have to do a recording. And the unit will record AC or DC up to 1,000 volts, and it can be done simultaneously. You can have some channels on AC and some on DC. The software, the PC software that comes with that, creates setups based on the problems. So you can actually go in, there's a drop-down menu, and you can say, I have a problem with equipment tripping out or lights flickering. And it will automatically create custom setup files that look for the phenomenon that caused those problems. It also will analyze waveforms up to 128th harmonic and let you know the harmonic directions. It does auto data analysis, and you can create custom data analysis templates on it. You can make these based upon your standards, and you can load them into the PQ analyzer as well. And this is a freeware. Okay? There is no extra cost for the software, and no dongles are required. Alrighty. And with that, I turn it over to you, Greg.
Thank you, Andy. At this time, the presentation portion of the webinar is officially concluded, but based on the feedback from last year's sessions, we're going to extend the Q&A session for another 30 minutes to answer all of your questions. If you have any questions, please submit them now in the Q&A box. For those that are leaving, when you close the webinar window, a survey will appear on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve future webinars. As we mentioned before, a copy of this webinar presentation will be emailed to you the next few days. A recording of this session will be available on our website at megger.com/webinars in the next 2 weeks. Our webinar landing page also contains a schedule of all upcoming webinars and recordings of all previous webinars. We would appreciate it if you could join us for our next webinar session in December, which is over a systematic approach to current transformer testing in the field. That'll take place on December 16th at 10 a.m. Central Time. Again, if you're looking for any more webinar information, you can find it at megger.com/webinars. Now let's get on to your questions. The first question we have is, what are some of the impacts of solar panels?
Okay. Well, with the solar panels that we're seeing that are installed, especially in residential areas, what we're seeing is one initial problem is high voltages they are creating. The high voltages are actually pushing more current through a lot of those motors and everything that are on the line. So we're seeing reports of failed air conditioner compressors as well as refrigerator motors as well. And these can be failing, every year or so, every year, every 15 months. So we're seeing many more failures due to these higher voltages that are being created. In addition, a lot of times when these solar panels are put on, they are put on only on one phase. So what they are doing is creating unbalance in the actual network. So we're seeing that as an issue. The unbalance also causes heating effects. And there's been some other complaints as well, such as electronics failing within 15 to 18 months, repeatedly, microwaves failing, things like that. And one of the things about solar tiles is they have very low impedance to them. So that when the sun changes, when you have a change in magnitude from a cloud or even just pollution or anything in there, I mean, it's not just visible light that affects these things. Their response is very fast. It's almost instantaneous. So what ends up happening is that you can get transients off these, and these transients can be continuous for a while, depending on what's happening with the light. And it's believed that these transients may be causing damage to some of the equipment, some of the electronic equipment that is out there. You don't really have this problem so much with wind power, because with wind, you have a certain amount of resistance as the turbine turns, so you don't have these instantaneous changes that you do see in solar. And of course, one of the other big problems you're going to see with solar and wind as well is the fact that we still, we use a radial system here, which was designed to deliver power from a source to a load in one direction. It was not designed for it to happen in the other direction. So with all these different sources and DGs being put on, we're actually seeing a lot of power reversals that are occurring. As these power reversals occur, you get a lot of tap changes on the transformers will start switching. As they switch, they're rated for several thousand switches, and these can actually fail very readily. So I know there's actually some work being done at looking at solid state tap changers. And of course, reversals of power can also create problems with protection equipment failing.
All right, the next question is, what is a high level of EMF? Can we assume the testing company will look for this and use the proper style CTs?
A high level of EMF, when you're looking at high levels of EMF, you're talking about the megahertz range. And typically, I wouldn't expect the testing company to necessarily look for this, but basically it's something just to keep in mind where you're in an area where you may have telecommunications equipment there or anything that could be producing this type of equipment or this type of frequency. But typically, I mean, it's high megahertz that you're looking at there.
All right, the next question is, you said each successive coil in a motor has more capacitance. Was it capacitance, or did you mean to say capacitive reactance?
Capacitive reactance, yeah. Basically, as the transient hits that coil, what ends up happening is that it's going to dissipate over the area of the first few coils. So you'll typically see the damage in the first few coils of the motor. That's really what I was getting at with that.
All right, the next question is, the lighting industry has been shifting more towards LEDs. Do you liken an LED to an incandescent light, so the flicker curves, etc., would apply directly to an LED?
No, it would not, because an LED light actually works off DC, not AC. So what you're seeing there is you're always going to have a rectifier that's running the LED, okay, whether it's built into it or whether it's separate. So actually what you'll see with an LED light is, since it has a power supply, you actually see harmonic content off that. And that can typically be, like I said, the 35 to 45 order harmonics. and the flicker really doesn't apply to that. If you do see flicker in LED lights, that's typically where you want to look at rapid voltage change or the possibility of interharmonics, creating some issues with that as well.
All right, the next question is, what causes triple harmonics?
Triplets, they are basically, like I said, third order, ninth order, and typically the nonlinear loads. And if you look at your harmonic orders or your harmonic profiles, it is basically computer loads that will be most commonly causing them. Those type of loads are addictive because you'll see the majority of third harmonic, then fifth will be next, then seventh, and it'll be a sort of a downward going curve. If you have other types of loads, such as a 6-pulse rectifier, you won't see third harmonic on that. You'll see a majority of fifth and seventh harmonic on that. So typically you're looking at computer type loads on those.
All right, the next question is kind of a long one. Let's see. What is the reason for not using flex CTs when in a high EMF area?
Some of the flex CTs is how they connect. Some of them will have a gap in them that actually just allows for the high frequency to get in where they connect. And it doesn't apply to all. Ours are pretty good with that. We don't have that issue. But with some of them, you have to look at how they connect. If they do have a gap, it's just safer at times to use the split cores because they don't have a gap.
The next part of the question is also, what does the high magnetic field do to the flex CTs, i.e. symptoms?
Basically, just some interference on them. And you might just see some noise on them.
Okay. Let me see here what we have next. What is the source of the PQ term definitions, i.e. overvoltage, undervoltage, used in the presentation?
Can you say that again?
What is the source of the PQ term definitions?
Oh, IEEE, is it 1159 or I'd have to get back to you with that. I forget the actual standard, but it is IEEE.
The next question is, where is the magnetic field coming from? Is it an external magnetic field?
When a current goes through a wire, it produces a magnetic field. So if you have an alternating current go through a wire, it creates an alternating magnetic field. So it's just a matter of physics. Anytime you have a current passing, you get a magnetic field. If you have a magnetic field that crosses a wire, you'll get a current induced in that wire.
All right. The next question is, what effects will transients voltage have on an isolation transformer?
Again, if the transients are repeated transients, will slowly degrade the insulation on them and can short out a coil over time. Or if you get a very large transient, you can end up shorting a coil out because of that insulation breakdown.
Can flicker impact the operation of controls for voltage regulators, etc.?
Well, flicker, keep in mind, flicker is when we refer to flicker, it's a light phenomenon. Okay, so really, I think what you're talking about can voltage fluctuations affect it. It's not really flicker because flicker always refers to lighting because it's light flicker, not voltage flicker. But voltage variations, yeah, they absolutely can, depending if they're large enough and frequent enough.
All right, the next question is, have you seen any connection between harmonics or other power quality issues at wind farms and failing transformer bushings?
Transformer bushings, that I haven't seen. I've seen issues with cable splices and things like that with the harmonics. I haven't experienced the bushing failures because of that. Doesn't mean this doesn't happen. It's just I haven't seen it.
Okay. Can current harmonics, specifically the fifth, have an adverse effect on transient voltage surge suppressors?
Can the fifth harmonic, which has a negative sequence, have an effect on transient voltage suppressors? I think it would depend on the type of transient voltage suppressor we're looking at. If it's a coil, then you can generate heat in it. Okay? Something solid state, I wouldn't think so, but anything with a coil in it would actually generate some heat in there. So I think that would be sort of the answer would be sort of depends on that one.
All right. The next question is, could you please re-explain the flat topping as it related to harmonics?
Okay, as when you have a nonlinear load, it draws current only at the peak of the waveform. So I have a voltage now that is sinusoidal waveform, and the current is being drawn just at that peak. If the current gets too high, the draw gets too high, the voltage can only support so much current that is pushing. When so much current is being pulled, the voltage dips at that instantaneous point. And since the current's being drawn at the peak of the waveform, we see that dip at the peak of the waveform. So that's where you get that flat topping effect that occurs. And like I said, that's typically due because the source isn't stiff enough to supply enough current at that point. So it might be an undersized transformer that's causing the issue, or something along those lines. But that's typically what's referred to when you see that flat top right on the voltage waveform.
Okay, let's see. Next question is, find one. Harmonic analysis. If there is a high harmonic in specific current phase for a wind farm, what could be the cause? Should I be checking at the power electronic devices of the turbine or the PCC?
Both. Check at both, but the actual inverters will generate high harmonic content, and typically, like I said, those will be seen around the 35th to the 45th. And it is those switching inverters that are creating those high harmonics.
Okay. Are there monitoring devices for these types of problems? Also, with these monitoring devices, is there any way they could isolate a problem from the plant so that it limits the damage to electrical wiring and equipment?
That I don't know.
Okay.
I don't know about the other monitoring devices.
All right, let me see. Scrolling through, a lot of people are asking for the presentation. And again, we will email that to you probably early next week. There's a question. 9 channels refers to what?
9 channels is the amount of channels we have on our MPQ 2000. There are 4 voltage channels and 5 current channels. So you can measure 3-phase voltage and 3-phase current, as well as neutral voltage, neutral current, and also ground current as well.
Is the unbalances the same thing as distortions, and how do they occur?
No, unbalance is not the same as distortion. Unbalance refers to an unbalance between the phases. Distortion refers to the actual waveform distortion due to the loads that are on them. Unbalance between the phases typically occurs because of unbalanced loads. You have higher loads on one phase than on the other, which will create the unbalance. You can also have it unbalances occur again due to solar tiles if they're hooked up to only one phase. Distortions occur from nonlinear loads such as computers, power supplies, anything with a switch mode in it, rectifiers. All these things will create distortion in the waveforms because they draw current only at the peak of the waveforms. They're not drawing it throughout the entire cycle evenly.
All right, the next question is, find it. Why are even harmonics not talked about as much as odd harmonics?
Because they're not as common. An even harmonic will occur is basically a sign that you have a piece of faulty equipment. A rectifier has opened somewhere. So they're typically not predominant. You won't normally see them on a system. When you do see them, it's an immediate flag that a piece of equipment somewhere has failed.
Let's see here. It's a long one. Let me read it first. If a utility customer, such as an industrial plant, exceeds IEEE 519 individual current harmonic limits, particularly the fifth, at the PCC between the customer and utility, yet it causes little additional voltage harmonics, does the site really need any additional investigation?
That's actually a talk that's actually happening. You see it a lot in IEEE, is that, that's one issue that they are discussing, is the fact that you may be exceeding the limit from IEEE 519, but if it's not causing a problem, do we really have to address it? And again, there's no, like I said, they're still talking that over. But when I look at the definition of power quality itself, the definition is basically the concept of powering and grounding sensitive equipment in a manner that's suitable to the operation of that equipment. When I read that, that sort of tells me if I don't have a problem, I don't have a power. If it's not causing a problem, there isn't a power quality issue. But again, this is something that they are debating in IEEE.
All right, let me see. Another one. If we are fed from a utility on primary 12 kV service, what kind of CTs and PTs are required to monitor harmonics?
Okay. Well, here's the problem when you look at something like that, because you're going to be using, you're going to be taking the measurements off a secondary of your PT and CT. So the secondary will typically be a low current. So you might have use a 5 amp CT on there because the current can be that low on the secondary. But with that said, one thing to keep in mind is that those PTs and CTs that are basically used in the substations to monitor this have a limited bandwidth, right? Which means that typically when you start getting above the 10th or the 15th harmonic, their accuracy is going to fall off because of that limited bandwidth. So when you do a harmonic analysis when you're looking at it from off a PT or a CT, you're really limited to the lower frequencies of those harmonics to look at because of the limited bandwidth of the transformers. Now, that doesn't always apply. You can get transformers that have higher bandwidths, but they are much more expensive.
What role will a transient voltage suppressor play with reducing these types of issues?
What type of issues?
I'm guessing the
transients.
Harmonics. We had that question come in. If you can follow up with a little more information on that one, we can get it answered. Let me see here. Scrolling down through the list. Do you see a certain piece of equipment failure resulting in 8th order harmonics?
That would typically be a sign that a rectifier somewhere has opened. I don't know what particular piece of equipment would do that, but it's definitely, you got a bad piece of equipment there if you have significant 8th order.
Does there appear to be growing power quality concerns with more power electronics being used in facilities?
Yes, absolutely. As you are, as more equipment is being used, you're adding more nonlinear loads, so you're getting some more distortions in there. As those distortions increase, especially as their frequency increases, because the higher switching rates now that you're getting, like I said, are putting higher frequency harmonics on them. And I mean, you'll hear people talk about looking at harmonics that are extremely high. Really what we're looking at is between the 35th and the 45th. And I mean, we actually go up to the 128th. But I mean, I've very rarely seen anything up that high. But as the harmonic frequencies increase, what that actually does, it can generate more and more heat in coils, anything that has a coil in it. And transformers, typically, they need to be derated. So you may have different K factors. So you have to look at the K factor of the transformer and check that. Actually, our unit does do K factor. So you can actually do that type of analysis as well to make sure that you are not overdriving the transformer.
Okay, let me see. questions about the equipment. I have one more, it's a little longer. Let me see. Oh, we haven't answer on that question we had a second ago. Let me find the original one. What the original question was: what role will a transient voltage suppressor play with reducing these types of issues? And the issues that he's referring to are the transients for the use of a TVSS.
Okay. Basically, they're resistant to change, the voltage change, so you will get a reduction. As far as how much reduction, I'm not sure, but keep in mind, anything that you put onto a system to correct one thing, you'll typically have an effect somewhere else. So you might see a lower voltage as well when you hook up something like that. So you have to just take into account that whenever you put any correction device on a system, you have to look at everything on that system to make sure that you didn't correct one thing and cause another problem. So yes, they will reduce transients, but you just want to be sure you're not lowering the voltage as well. That could create problems.
Okay. Do you find small wall wart power supplies for laptops and other equipment to contribute to significant levels of harmonic distortion, especially when there are a lot of them, like in an office environment?
It all depends. You're exactly right. It all depends on the quantity of them. Individually, they don't have that much effect because they're not drawing that much current. But as you get more and more, yeah, they're going to draw more and more current. And as they draw more and more current, the harmonics will become more significant because as the harmonic currents increase, eventually they're going to start affecting the voltages. So that's why it's important to look at both current harmonics as well as voltage harmonics.
All right, let's see if we can find another question.
And by the way, will typically be where you see that signature of third, fifth, and seventh, where the third will be the highest, and the fifth, and the seventh. That's pretty much category. That pretty much shows you that you're having those type of loads.
This one's really specific. What is the effect of current distortions on elevator motors, or I guess motors in general?
As you have current distortion, what will happen is what I talked about before with the skin effect. As the magnitude of those harmonics increase and the frequency increases, you will generate more heat in them because you're increasing the skin effect, which is pushing the current more to the outside of those motors. So they will heat up. And obviously, the more heat you get, the faster they will deteriorate.
Okay.
So,
all right, next question. Let me see if I can shorten it a bit. You can connect the monitoring unit on the medium voltage side for power quality. The question is, how can I connect the power quality directly to the medium and high voltage side?
The only way to do that is by using PTs or CTs. You have to step it down. You can't connect directly to them.
Okay. That may be the last question. I think everything else is related to getting the presentation and about the MPQ 2000.
Okay.
All right. Well, with that, we'll go ahead and close out the Q&A session, and the webinar is officially closed. Again, once you log out, you will be sent a survey, and if you could fill that out, that would be great, and we can continue to improve our webinars as we go on into next year. And be looking out on our website at us.megger.com/webinars. We are currently working on our 2017 schedule, and it should be out probably mid-December. And with that, we will end the webinar. Thank you very much, everybody, and we will be sending you an email with the presentation and with a link to the video as well. Thank you.
Thank you.
Perfect.
Good job, boys.
Thank you very much.